Because of Election Day on Tuesday, November 5th, I am delivering this lecture virtually and asynchronously. So I've recorded a video of me going through the lecture just as I would in class. You will also find on Carmen the PowerPoint slides that go with this lecture. So what I would encourage you to do is to print out the slides and then go through the lecture and take notes just like you would if it were a real live lecture. I'll be back in class on Thursday and we can go over any questions you might have about this material. Today's lecture is going to cover sections 9.4 through 9.6 of our textbook. So we have been using Lewis structures to great effect. We've found that we can draw these dots around atoms that represent valence electrons, and that gives us a Lewis structure. And from the Lewis structure, surprisingly, we can predict things like the shape of a molecule, whether the molecule is going to be polar or not, even things about how strong the bonds are going to be. But the question is, why does it work? What is the basis of the Lewis structure model? What is the basis of the octet rule? And to get at that, now we're going to bring in elements from Chapter 6. Remember back in Chapter 6 we talked about atomic orbitals. So we're going to marry, if you will, the atomic orbitals from Chapter 6 with the Lewis structures from Chapter 8. Together, what we're going to find is that they show us that when we have atomic orbitals that overlap, that concentrates electron density between nuclei and forms bonds. We'll also see that just like an atomic orbital, a bond can hold two electrons of opposite spin. Okay, well, let's get started. So if we were to think about the bonding in the simplest molecule possible, the bonding in a hydrogen molecule, the idea is that we have two hydrogen atoms, and each of them has one electron in the 1s orbital. Now, if we were to allow those two orbitals to overlap by bringing the atoms closer together, what we would find is a mixture of attractive and repulsive electrostatic interactions. The electrons and the nuclei, being of opposite charge, are going to attract each other. So if we can put a lot of electron density between the two nuclei, that's going to be favorable. That's going to lower the potential energy of the molecule. But we also have to be cognizant of the fact that the electrons are repelled from each other and the nuclei are repelled from each other. So we can do this kind of energy graph as a function of the distance between the two hydrogen nuclei, the internuclear distance, if you will. And what we see is out at very far distances, when the hydrogen atoms are well separated from each other, there's sort of minimal overlap of the orbitals, and we asymptotically approach what we're calling zero energy. Zero energy here would refer to the energy of two hydrogen atoms that have no interaction with one another. As we bring them closer together, we say that the potential energy starts to drop. It goes down, and the reason why it's going down is because of the electrostatic attractions between the negatively charged electrons and the positively charged nuclei. And in particular, that would only happen if we're building up more electron density between the two nuclei. Okay, and that's what we're going to call a bond, a sigma bond anyway. Finally, we get to this minimum energy for a hydrogen molecule that occurs at 0.74 angstroms. Okay, and that's the optimal distance. That's what we call the bond distance. And if we keep moving the nuclei closer and closer together, what we'll find is now the energy starts to go up. And eventually it becomes very unfavorable, a very positive energy. And the reason for that is largely because of the repulsions between the nuclei, which are getting too close to each other. You know, the other thing, you might say, what about the repulsions between the electrons? That's also kind of built into the system, but ultimately that's what's going to limit us to putting only two electrons in a bond. Okay, because electrons are kind of special. They have quantum mechanical properties. They behave in ways that are not altogether intuitive. So we'll see that this bonding is optimal when we have two electrons in the bond. Okay, let's look at another molecule, another diatomic molecule. This one a little bit more complicated. Let's think about the chlorine molecule, Cl2. Now, if we look at the Lewis structures up here at the top, we can see that each chlorine atom has 7 valence electrons. And when we put them together, they each share 1 electron with its neighbor, and that forms a bond. And in that way, they satisfy the octet rule. If we were thinking about the electron configuration of chlorine, we would see it here. It's got a neon core and then 3s2, 3p5. 3s subshell is filled. The 3p subshell has 5 out of the possible 6 electrons in it. So remember that there are 3 different orbitals in the 3p subshell, and one of them, let's arbitrarily call it the pz orbital, is going to be only half filled. So if we now overlap the 2 half-filled orbitals on neighboring chlorines, we can get this picture, and we can see that we can form a bond by once again overlapping 2 half-filled orbitals, 2 orbitals that have 1 electron. And so that's in some ways very much like what we saw with hydrogen. The only difference is here we're overlapping p orbitals instead of s orbitals. You know, it turns out that we can overlap various kinds of orbitals. They don't even have to be the same. In a molecule of hydrogen chloride, then we are going to overlap a 3p orbital on chlorine, which we just saw has 1 electron, and the 1s orbital on hydrogen, which has 1 electron. And once again, we're going to get then an attractive interaction that leads to a covalent bond. And there's going to be 2 electrons that populate that bond. Now that we have the basic idea of orbitals overlapping to give us a bond, let's consider the situation in more complex molecules. And to do so, we're going to have to introduce something called a hybrid orbital. Let's increase the complexity just a little bit, going from a diatomic molecule to a molecule that has 3 atoms. Here, beryllium difluoride. Now, if we think about our orbital overlap picture in beryllium difluoride, concentrating on the central beryllium atom, we'll see that we've got a couple of questions. First of all, will the orbitals on the beryllium now overlap with just one fluorine neighbor or with both? Or maybe a mixture of the 2. And secondly, when we look at the electron configuration for a beryllium atom, we see that it has 2 valence electrons, which is enough to fill up the 2s subshell, but leave the 2p subshell empty. So there aren't any orbitals that have 1 electron that are poised to make a bond. So how are we going to get bonds in beryllium difluoride? Well, the approach that valence bond theory takes is to take the 2s orbital and one of the 2p orbitals, specifically the one that's pointing at the fluorine atoms, and mix them together to form hybrid orbitals. Okay, and we see that each hybrid orbital has a big lobe of electron density that points on one side of the beryllium. This top one has a big lobe that points to the right, and a small lobe that we're largely going to ignore that's pointing to the left. Whereas the other hybrid orbital is the opposite. It has a large lobe that's pointing to the left. So if we draw them both together here and ignore the small lobe, we get sort of 1 electron orbitals that are pointing in opposite directions. And we're going to call these orbitals sp hybrids. We call them sp hybrids because they're made from 1s and 1p orbital. So sp hybrid is the name, tells us which orbitals went into making it. Now we can put the 2 electrons, the 2 valence electrons in beryllium, into these sp hybrids. And because we now have orbitals that are pointing at the fluorine that have 1 electron, and we have a 2p orbital on fluorine with 1 electron, we can get a bond, much like we did in the Cl2 case. The overlap of the sp hybrid orbitals on beryllium with the fluorine p orbitals is such that it's going to be optimal overlap if we have a linear molecule, that is a 180-degree fluorine-beryllium-fluorine bond, which is exactly what was predicted by Vesper. But we do want to keep in mind, and it'll be important later, that we do still have two p orbitals on the beryllium that are not involved in the hybridization. In this molecule, they're empty, and so therefore they don't exert much impact on the structure of the molecule, but we'll see later when they're filled, they do. What about if we mix together three orbitals? Specifically, an s orbital and two of the p orbitals. If we mix those together, those three orbitals, we get something called an sp2 hybrid orbital. And it looks kind of like the sp hybrid with a big lobe on one side and a small lobe on the other. But the key point here is that the large lobes of these sp2 hybrids point toward the corners of an equilateral triangle, okay, which is the perfect geometry if we're going to have a trigonoplanar molecule. And that's exactly what we have with BF3. Now we've replaced the beryllium with a boron and added a fluorine. Now boron has 3 valence electrons, but if we form sp2 hybrids, we can put the 3 valence electrons, one in each of the sp2 hybrids. So now we have orbitals containing 1 electron that point toward the corners of an equilateral triangle, which is the perfect geometry to get bonds in the BF3 molecule. Can we keep going? Yes, we can. We can mix together the s orbital and all 3 of the p orbitals, and when we do that, we get something called an sp3 hybrid. And the key takeaway feature of an sp3 hybrid orbitals is the large lobes point toward the corners of a tetrahedron. Now, if we go to a molecule like methane, CH4, right, which has this Lewis structure, so if we look at the electron domain geometry or the molecular geometry, they're both going to be tetrahedral. If we look at the central carbon atom, right, it has 4 valence electrons. So if we were to make sp3 hybrids, right, and we get 4 of them because we're mixing together 4 atomic orbitals, so we get 4 hybrid orbitals. We put 1 valence electron in each, and now we're perfectly well set up to make this tetrahedral molecule by overlapping sp3 hybrid orbitals on carbon with 1s orbitals on hydrogen. Next, let's take a look at the water molecule. And we're going to look at the bonding and the geometry of a water molecule from 2 different perspectives. Let's start by saying that you're skeptical about these hybrid orbitals. And you want to say, well, I'm not sure that they really exist. And if I think about water and the central oxygen specifically, it has 6 valence electrons. And that happens to be just the right number so that I can get 2 p orbitals on the central oxygen with 1 electron each. And those p orbitals would be ready to make a bond with the 1s orbital on hydrogen. Now, those 2 p orbitals would be at right angles to each other. Here, I'm just arbitrarily calling one the 2px and the other the 2py. And if I did overlap just those atomic orbitals with the hydrogens, then I would get something that looks like this. Because the 2p orbitals are perpendicular to each other, that means this hydrogen-oxygen-hydrogen bond should be 90 degrees. Okay, so that's an experimental thing that we can measure and compare it to our bonding theory. If, on the other hand, we were to assume that we had hybrid orbitals, specifically sp3 hybrid orbitals, then what we would see is that 2 of the hybrid orbitals are doubly filled. So those actually are not going to make bonds with anything. And then 2 of the orbitals which are occupied by only a single electron. And those could overlap with the 1s orbitals on hydrogen. Now, in this scenario, we expect the hybrid orbitals to be pointing toward the corners of a tetrahedron. So now, the hydrogen-oxygen-hydrogen bond angle should be 109.5. That's the ideal bond angle for an octahedron. Now, if we look at a water molecule, what we see is the bond angle is 104.5. It's not exactly 109.5. We talked earlier that a part of the reason for that might be that the lone pairs, the non-bonding pairs, take up more space. But in any event, it's a lot closer to 109 than it is to 90. So this tells us that, this hybrid orbital picture is a better representation of what's going on than just individual p orbitals forming bonds to the hydrogen atoms. So one of the things we're going to have to do, this is going to be on the homework, it'll be on the midterm, I'm sure, is to look at a molecule and assign the hybridization at a given atom. How do we do that? Well, a lot of it we've already been practicing. You first do the Lewis structure. Step 2 is you use the VSEPR model and assign an electron domain geometry to the atom where you're trying to assign hybridization. Once you've done that, it's pretty straightforward. If there's 2 electron domains, we need 2 hybrid orbitals, so we pick sp hybridization. If there's 3 electron domains, we need 3 hybrid orbitals, and we'll pick sp2 hybridization. If there's 4 electron domains, we need 4 hybrid orbitals, and we go with sp3 hybridization. I do want to stress here, though, that this is the electron domain geometry, not necessarily the number of bonds the central atom makes. We could also encapsulate that same philosophy in this table here. All right, so if we have linear electron domain geometry, with only 2 electron domains, like we see here, then we get sp hybridization. If we have a trigonoplanar electron domain geometry with 3 electron domains, then we get sp2 hybridization. And if we have 4 electron domains and a tetrahedral electron domain geometry, we get sp3 hybridization. So here are a couple molecules. What I would like you to do now is to pause the video and complete this table. Predict the hybridization at the nitrogen atom in ammonia and the central oxygen atom in ozone, and then come back and I will go through the answers. Okay, welcome back. Let me walk you through the answers and see if they agree with what you worked out on your own. Let's start with the ammonia molecule. So the Lewis structure for NH3 is shown here. This molecule has 8 valence electrons. So we get 3 bonds to the central nitrogen atom and 1 non-bonding electron lone pair. That means the electron domain geometry at nitrogen is tetrahedral because there are 4 electron domains. And therefore, the hybridization must be sp3. If we look at ozone, its Lewis structure looks like this. We have now 3 electron domains at the central atom. A double bond, a single bond, and a lone pair. So the electron domain geometry is trigonoplanar, 3 electron domains. And when we have 3 electron domains, we need 3 hybrids, so we're going to get sp2 hybrid orbitals. Okay, before we leave hybrid orbitals, I want to say just a little bit about the situation with hybridization in molecules where we have a central atom that has more than an octet. Remember, right, we have these trigonal bipyramidal molecules with 5 electron domains. We have these octahedral molecules with 6 electron domains. How are we going to do that with just an s and 3p orbitals? The answer is not very well. So what valence bond theory tends to assume is let's bring in the unfilled d orbitals from the same shell. And that means if we were to look at a molecule that have 5 electron domains, like SF4, we could say the hybridization is sp3d. If we had something with 6 electron domains, like SF6, it would be sp3d2. So this is what valence bond theory, which goes back to the middle of the 20th century, if not a little earlier, would tell us to do. Nowadays, scientists can do pretty accurate calculations of which orbitals are involved in the bonding, and those calculations show us that really the d orbitals are making a very small, if almost negligible, contribution to the bonding. So this picture is probably not that close to reality. What that means for you is that we're not going to talk about hybridization at atoms that go beyond the octet rule, that have more than an octet of electrons. To do that, you really need molecular orbital theory, which we'll touch on later, but not really in enough detail to cover molecules like this. So that's something that you'll have to wait until you get to a higher level chemistry course to get into. Okay, now let's move on to section 9.6, where we talk about multiple bonds. Thus far, the picture that I've been painting is one where you have two orbitals that, let's say, point toward each other on different atoms. They overlap, they give you this covalent bond. And we've said that bond can hold 2 electrons. So that's enough to give us a single bond. But we know that there are Lewis structures where we might have double bonds or even triple bonds. So where do those come from? In order to explain those kinds of bonds, we need to introduce a new kind of covalent bond. The covalent bonds we've been talking about thus far are what we call sigma bonds. And here I show, for example, the sigma bond in the Cl2 molecule. But this could also be the sigma bond between an sp2 hybrid on boron and the p orbital on fluorine. Right? It could be a variety of things. The characteristic features of this sigma bond are a direct head-to-head overlap of the orbitals, and that leads to a lot of electron density on the internuclear axis, the line that connects the two nuclei. These kinds of bonds have a cylindrical symmetry around the bond. But the other kind of bond that we're going to encounter, they're called pi bonds. And pi bonds are formed when you have sideways overlap of typically p orbitals. That's what we're going to talk about here. Never s orbitals, but mostly p orbitals. And so if you have two p orbitals that are parallel to each other and side by side, they can overlap in this region above and below the internuclear axis. We don't have any electron density actually on the line between the two nuclei, but we do get this overlap to form a bond above and below the internuclear axis. So that's what we call a pi bond. And when we have multiple bonds, we're going to see that we have both sigma and pi bonds present. So going back to, the Lewis structures, we can do something that is very simple. If you look at any molecule, and here are 3 examples, and you see just one line connecting the 2 atoms, that is a single bond, that must be a sigma bond. If you have multiple lines, 2 lines for a double bond, or 3 lines for a triple bond, we still have a sigma bond, but the extra bonds come from pi bonds. So a double bond is 1 sigma bond plus 1 pi bond. A triple bond is 1 sigma bond plus 2 pi bonds. So let's just start with something kind of simple. Let's look at a couple of molecules, C2H4, which is called ethylene, and CH3CN, which is called acetonitrile. What I would like you to do is draw out the Lewis structure, and then you should be able to, from the Lewis structure, tell me how many sigma bonds and how many pi bonds there are in that molecule. Why don't you go ahead and pause the video, work through the problem, and then come back and we'll go over the answers. Welcome back. All right, let's start with the C2H4 molecule. The Lewis structure for this molecule is something like this. Right? Each carbon has 4 valence electrons, and each hydrogen has 1. So there's 12 valence electrons in this molecule, and that's enough to make 6 bonds, which I've drawn here, and that puts a double bond between the 2 carbon atoms. Now, if we count up the bonds, we can see that we have 1 sigma bond between carbons. Anytime you have 2 atoms bonded together, there will always be 1 sigma bond. Then we have 1, 2, 3, 4 carbon-hydrogen sigma bonds. So in total, we have 5 sigma bonds. And then we have this multiple bond here. We have this double bond. So there's 1 carbon-carbon pi bond. Right? So 5 sigma bonds, 1 pi bond. In this molecule, acetonitrile, the Lewis structure looks like this. You may have drawn it in other different ways, but this is going to be the way that gives you the lowest formal charges. This is the optimal structure of this molecule. And what we can see is that we have one carbon-carbon single bond, 1, 2, 3 carbon-hydrogen single bonds, and then 1 carbon-nitrogen single bond. So this molecule also has 5 sigma bonds, and it has 2 pi bonds because the carbon-nitrogen bond is a triple bond, and the triple bond is always going to be 1 sigma and 2 pi's. So this molecule has 5 sigma bonds and 2 pi bonds. Let's now think about the orbital overlap that would give rise to a pi bond. And we want to come back to this C2H4 molecule, ethylene. All right, so we just saw its Lewis structure. We noted that it has 1 sigma bond and 1 pi bond between carbons. If we think about the electron configuration of carbon, it has 4 valence electrons. So this would be an isolated carbon atom, electron configuration. And then over here on the right, we would have the electron configuration in this molecule. One of the things you'll note is I've drawn it as sp2 hybridization. How did I know sp2 hybridization? Well, we just went over that, right? If we have 3 electron domains at carbon, which we do, then the electron domain geometry is trigonoplanar, and we need 3 hybrid orbitals, so that gives us sp2 hybridization. That means there's 1 2p orbital that's left over that is not involved in forming hybrids. And in carbon, we have just the right number of electrons that we can put 1 electron in that unhybridized 2p orbital. It happens to be the 2p orbital that is perpendicular to the plane of the molecule. Right? This is a flat molecule. So let's now take a 3-dimensional look at this molecule. Okay, what's drawn here in the upper image would be in purple the sp2 hybrids, and then in kind of this reddish pink color is the unhybridized 2p orbital. Now we can add in our hydrogen 1s orbitals, which are shown in blue in the middle image. And when you look at this image, you can see that we're getting a carbon-carbon sigma bond from overlap of the hybrid orbitals. And at each carbon, we're getting 2 carbon-hydrogen sigma bonds from overlap of the sp2 hybrids with the 1s orbital on hydrogen. And then finally, in the lower image, we see how if we allow these 2p orbitals that are perpendicular to the rest of the molecule to overlap, we can get our pi bond. And that pi bond is what gives us a double bond between carbon atoms. If we were to go to acetylene, that is C2H2, it has the Lewis structure I show here. Right? So this has got a triple bond between the 2 carbons. And if we look at the electron domain geometry at either of the carbons, we would see there's 2 electron domains, so we need sp hybrids. We still, though, however, have 4 valence electrons on carbon, so once we put 1 electron in each of the sp hybrids, there are 2 electrons left over, and they go into the unhybridized 2p orbitals. So that's the picture we see at the top. Purple orbitals are the sp hybrids, and the reddish pink orbitals are the unhybridized 2p orbitals. So you can see overlap of the hybrids gives us a carbon-carbon sigma bond. And here in the middle image, overlap of the hybrid with the hydrogen 1s orbital gives us 2 carbon-hydrogen sigma bonds. And then finally, if we overlap the unhybridized 2p orbitals on each carbon, we get 1, 2 pi bonds, which are perpendicular to each other. They're at 90-degree angles to one another. And that combination, 1 sigma and 2 pi bonds, gives us the carbon-carbon triple bond. Here's a question for you. We're going to look at this molecule, acetic acid, and what I would like you to do is to look at the 3 central atoms in this molecule, 2 carbons and 1 oxygen. I want you to predict the molecular geometry at each of those atoms, and then also tell me what is the hybridization of the atom at each of those spots. Pause the video, fill in the table below, and then come back and we'll go over the answer. Well, how'd you do? Good, I hope, but let's go over the answers and see if your answers match mine. Let's start with this carbon that is in the green square here, right? That one has 4 bonds to it, so it has 4 electron domains, which means its electron domain geometry is tetrahedral, and that also means its molecular geometry at that carbon atom is tetrahedral. And because the electron domain geometry is tetrahedral, the hybridization is going to be sp3. Now let's look at this other carbon atom, which is in the blue circle, and that one has 1, 2, 3 electron domains. So 3 electron domains means the electron domain geometry is trigonoplanar, and that means the molecular geometry here is also trigonoplanar because there's no non-bonding pairs to change things up. And if we have a trigonoplanar electron domain geometry, then our hybridization must be sp2. Finally, we have the oxygen atom. The oxygen atom has 2 bonds to it, so 2 bonding domains and 2 non-bonding pairs. So there are 4 electron domains, which means the electron domain geometry is tetrahedral, just like the first carbon. Now the molecular geometry here is bent because 2 of the electron domains are non-bonding. But the hybridization is determined by the electron domain geometry, not the molecular geometry. So the hybridization at this oxygen is sp3. Okay, well, I hope you got that. If not, go back over some more molecules until you can get it. One thing I want to say about pi bonds and sigma bonds, how they differ from each other, has to do with rotations about the bond. Let's go back to our 3-dimensional shape of our acetic acid molecule, which is shown here, okay, where we now see the shape a little bit better. If I were to look at this carbon-oxygen double bond, what I can say about this double bond is that molecules do not rotate. They're not free to rotate around a double bond. And the reason why is because here we're seeing, the side-on pi overlap between parallel p orbitals. But if I rotate around the bond, then what that's going to do is it's going to now break that overlap. And so for a molecule to rotate around a double bond, you have to break the pi bond first before that can happen. I'm not going to go into the details here, but in the textbook, there's an example about the molecules that are responsible for your vision and how when certain wavelengths of light hit those molecules, they break bonds and allow them to rotate where they couldn't before. That changes the shape in such a way that sends a signal to your brain, signaling that you've just experienced a photon of light. In contrast, if we were to look at this carbon-carbon bond, this is a single bond, right? There's no pi bond here. And remember that the electron density in a single bond, it's spherically symmetric. So there's no barrier for this molecule to rotate around this bond. So it means these hydrogen atoms are constantly spinning around and not locked in place. Okay, the last topic I want to get to in this section, it's kind of an important one, is to come back to the idea of resonance. Right? Remember in Chapter 8, we talked about molecules like the nitrate ion, where you can draw resonance structures that are different from each other but equivalent. And when we go back and look at those, what that really makes them different from each other is the location of the pi bonds. So here in nitrate, we could have a double bond going up, a double bond going to the left, or a double bond going to the right. So what exactly does that mean? Well, let's view this molecule now through the lens of valence bond theory. We can say that at the central nitrogen atom, it's got 3 electron domains, so we have sp2 hybridization. And there's 1 unhybridized 2p orbital at the nitrogen. And that's going to be perpendicular to the plane of the molecule, and that would be available to form a pi bond, which is good because we do have a pi bond in the molecule. Now at the oxygens, which are really on the periphery, they can also have a p orbital that's oriented in the same way. And so it is the overlap of the orbitals on the oxygen and the central nitrogen ultimately that's responsible for the pi bonding. But let's look now at the overlap of orbitals that give us sigma and pi bonds. So here I'm showing the sp2 hybrids on nitrogen. And for the sake of argument, let's say that the oxygen is also sp2 hybridized. If we did that, we would see that the hybrid orbitals can overlap with each other to form a sigma bond. And those sigma bonds are localized in space. They're not going anywhere. They're between the central nitrogen and each of them one of the outer oxygen atoms. But the pi bonds, what's the orbital overlap there? Well, if I were to take one of those resonance structures and draw the bonding, I would get non-bonding electron pairs on these two oxygens, and then I would get a pi bond between nitrogen and this oxygen. But I could draw another resonance structure where the pi bond might go this way, or the pi bond might go to the other oxygen here in the back. And so what we ultimately have is we have only one pi bond, but that pi bond is smeared out over all three NO contacts, right? And we can see the electron density in that pi bond makes something like the shape of a Y above and below the molecule. Okay, so this is what we mean by a delocalized pi bond. And that's why the bond order here is, stronger than a single bond, but not as strong as a double bond. Here we have the one pi bond spread over three different contacts. That would be a bond that's 1 1/3. We can also look at this molecule benzene, which I said before is quite important in organic chemistry. And in that one, remember, we can draw two different resonance structures. It's a flat molecule, and in the central part of the molecule, we have a hexagon of carbon atoms. And we can, make two different choices about where the double bonds go within that molecule. Now, at each carbon, because there are 3 electron domains, we would say it's got sp2 hybrid orbitals there. That leaves 1 unhybridized p orbital per carbon. And something about those 6 unhybridized 2p orbitals gives us, the pi bonds. But we can see from the Lewis structure, there's not 6 pi bonds, there's only 3. Here's a picture which shows us the sigma bonding network in benzene, and then our unhybridized p orbitals. But then thinking about how those p orbitals might overlap to form pi bonds, we can think about a picture where in one resonance structure it looks like this, and in the other resonance structure it might look like this, right? So they're just different in the placement of where the double bond is. The best picture, the true picture, is one where actually that pi bonding is totally delocalized around all of the hexagonal ring, okay? So we have 3 pi bonds, but they're spread out or shared by 6 different carbon-carbon neighbors. So in this case, we can say the bonds are about halfway between a single bond and a double bond. And when we look at their bond length or their bond strength, we would see that that's basically true. Okay, let's finish today's lecture with one more example. We talked earlier about the acetic acid molecule. So what I want you to do is to think about when acetic acid acts like an acid, it gives up an H+, and that leaves behind this acetate ion, CH3COO-. So I want you to draw a Lewis structure for this ion and determine the hybridization at the carbon that's bonded to the oxygens. I want you to tell me how many sigma and pi bonds there are in this molecule. I want you to tell me if this molecule does or does not exhibit delocalized pi bonding, and then tell me something about the strength and the length of the carbon-oxygen bonds. Like before, I want you to pause the video, work through the answers, and then come back and I'll go over them. Okay, here we go. Well, let's start by drawing the Lewis structure. We had the Lewis structure before, so it would be easy to go back in your notes and just make a little bit of a tweak to this, right? We lost an H+, so that means where we did have an OH bond here, now we have just a non-bonding pair of electrons, and the whole molecule has a negative charge. But now that the hydrogen atom is gone, the electrons that go into this pi bond could equally go to either oxygen, right? So we can draw a resonance structure where we put the double bond either to the right or up. So we do see that we have resonance structures. if we looked at the hybridization of this carbon that's bonded to the oxygens, we can see that in either resonance structure, it has 3 electron domains. So that means its electron domain geometry is trigonal planar, and that means that the hybridization must be sp2. If we count up bonds, we can see that there's 1, 2, 3 carbon-hydrogen sigma bonds, 1 carbon-carbon sigma bond, and then 1, 2 carbon-oxygen sigma bonds. And there's one and only one pi bond, and that's a carbon-oxygen pi bond. It's pointing in a different way in the 2 resonance structures, but we only look at one resonance structure to do this counting. If we ask the question about delocalized pi bonding, the answer is yes. When we have this kind of resonance and the pi bond is moving around, that is the telltale sign of delocalized pi bonding. And what that means is each carbon-oxygen bond is equivalent to the other. They're stronger and shorter than a single bond, but weaker and longer than a double bond. So we expect a bond length that's intermediate between a carbon-oxygen single bond and a double bond. Okay, well that's the end of the lecture. Hopefully this will be useful to you. Like I said, we'll have in-class lecture again on Thursday, and if you have questions, please let me know and we can go over those in class.